Hey chemists, so we finished our Ester practical. We had a great time. We made our product, and now it's an opportunity for us to write our last practical report for the year. So this video is just to give you a little bit of assistance with that writing process, just to talk you a little bit through the task sheet. Okay, so essentially what we've ended up with is hopefully some results. The first thing that we want to do when we're writing our report is just get straight into the calculations. Okay, so just to give you some assistance with this, I've stepped it out, not giving you very much structure, but just giving you an idea of what you need to do. So first of all, you want to calculate the number of moles of carboxylic acid and alcohol used. Now, in order to do this, you want to use the density data that I've given you down here. So the carboxylic acid was ethanoic acid, which is acetic acid, the same thing, and the alcohol we used is ethanol. Now, the ethanol is basically 100% concentration, and the ethanoic acid, looking at the bottle, it says greater than 80%, and at the back, at the side, it says 99.7% purity. So essentially, we're assuming that it's 100% concentrated, which probably isn't the case. There'll be a few impurities there, but that's an assumption that we're going to make when we're calculating the concentration. So that's something already that we can talk about in regards to systematic error. So what we're going to do is work with the density. It's really easy, so because it's 1 gram per mil. So essentially, when we measured out, oh, my cat just jumped up. When we measured out a certain volume of the carboxylic acid, so we had 18 mil, we can just basically say the mass of the the mass of the ethanoic acid is equal to the volume times by the density. So guys, that's really easy because the ratio is 1:1 in this regard. Ethanol is slightly different. So when you're calculating the mass of ethanol that was weighed out, it's going to be the volume multiplied by this density here. So the mass is going to be slightly different. Okay. From that mass, we can obviously calculate our number of moles, which is using mass divided by molar mass. Okay. Once we've calculated the number of moles of both, we use the equation and mole ratios to calculate the theoretical number of moles of ester and convert that number of moles into a mass, which is in grams. Okay, so moles and grams. The percentage yield of ester, essentially the mass that you're expected to obtain, divide that by the expected. Okay, so percentage yield is the mass obtained. So in your experiment, divided by expected mass times 100. Okay, so basically that's what you're going to end up with in regards to a percentage yield. Now, something I'll tell you guys is the percentage yield is not supposed to be 100%. And if I go back down here to the task sheet, which is actually relatively detailed this time around, analysis and evaluation, it's saying to get a, obviously we're aiming for an A, aren't we? Explains clearly 2 reasons for the poor yield of ester and is able to accurately describe how the yield can be improved. Now, you're not going to get 100% yield. If you Google this type of esterification, and it's called Fischer esterification, so the production of that carboxylic acid here. Oops, lost it. Hold on. So Fischer esterification, there's heaps of information about it. So have a look, have a bit of research. If you look at the sector lesson that I've put in for the 4th of September, there's a few videos, Khan Academy video, and this YouTube video is quite good, just describing basically what's happened. For mine, if you can recreate or re-describe using these videos, you'll have a really, really good assignment. So utilize those resources. There's plenty of stuff out there to do. Google the expected percentage yield for this experiment, and you'll find that it's not 100%. It's closer to 65, I believe. When you find that information, make sure you're referencing it. Okay, so now we've done our calculations, we've got our theoretical percentage. I'd start working on the rest of the report. You want to make sure, just a basic aim, and you've got information in regards to the ester. So have the ester data, including the name, the odor, the boiling point range of the ester, and the other components, and the yield that you have obtained. So that's the table that you're going to make, and then you have your calculations. If you want to handwrite your calculations and upload them, that's absolutely fine, go for it. You don't have to type them. It does look a bit neater typed though. Interpretation and evaluation is not just this part here. This is basically what I've given you this other sheet for, this one. So it's explaining each part of the experiment. And the earlier we do that, the better, because it's fresh in our minds. So explain the purpose of the reflux. So have your experimental setup, get a diagram from the internet, also put in your pictures that you took from the practical. The more diagrams, the better, I think, for this kind of thing. So explaining everything, explaining why this is set up this way, what's the purpose of the condenser, what's the purpose of each of the components, okay? Obviously the acid and the alcohol make the ester. Talk about the reaction conditions, the fact that you need that acidic conditions, so that's why the sulfuric acid is needed, what the purpose of the boiling chips are, all that kind of stuff. You can talk about how successful it was using the Bunsen burner with the tripod setup to get that temperature control for that gentle boiling. You can talk about how long you heated it up for, 30 minutes. You might find that it's probably better to heat for longer, and that's part of the weaknesses or the limitations of the practical, the fact that we didn't reflux probably for as long as we would have liked, but that's the time restrictions we've got in a high school. Distillation, this picture's not fantastic because we don't use a fractionating column, but what's the purpose of the distillation? So explain that setup there. The collecting flask, you're putting a stopper on it so the fumes don't escape. Link distillation and separation to differences in boiling points. So distillation, the big thing is you've got multiple species in that flask and you only want to get your ester. So you're using the boiling points of the different components in order to achieve that. Now, I've probably put this the wrong way around because the distillation was at the end. So this part should be beforehand, okay? So that's my mistake there. The isolation procedure is all of the washing. So adding the water, getting the separation of the two layers. Now we had an issue where at this point we were expecting to get the organic layer and the aqueous layer. When that didn't happen, so we can't really speculate as to why that might be, but we can write that didn't occur. It may have been because the ester wasn't cooled for long enough, it didn't lower. It may be because the particular ester that we have is relatively polar when it should really be non-polar in that organic layer, but that's only speculation, but you can describe what we saw. It wasn't until we added the sodium carbonate solution that we got those two separate layers, those distinct layers. And because we couldn't discard the aqueous layer, which contains the acid, we had that huge kind of vigorous reaction with the sodium carbonate, which led to a few mistakes happening in the lab. So that's something that we can talk about there. Talk about that separation technique with the separating funnel. What's the purpose of adding the sodium carbonate? What does that actually do? Okay. Make sure you're identifying what's in the flask. So after you refluxed, going back to the first part of the reflux here, what was in the flask? So it says here you should have 2 reactants, 2 products, and the catalyst, which is the sulfuric acid. Why are each of them present? You talk about the equilibrium reaction, okay? So explaining that, all right? What is an equilibrium? When that's being established, what does that mean? You know, you've got the forwards reaction, the backwards reaction, all that type of stuff. And what we're trying to do is make sure the forwards reaction is favored, okay? And we can do that by siphoning off one of the products. One of the products of the reaction is water. You get the ester and water. If you siphon away the water, get rid of it, that reduces the reverse hydrolysis reaction happening, going back to the carboxylic acid and the alcohol. So we're doing a few tricks to try and prevent that as much as possible. Talking about solubility. Solubility is a huge part of this experiment because we're talking about the polar and non-polar layers. The organic layer is the non-polar, the aqueous layer is the polar layer. So you're really talking about what species are present in what layer and really describing those secondary interactions to make that so, and diagrams and all of that kind of thing really help accentuate those points. Explain the purpose of the addition of water, so that the washing steps, the purification, referring to the equation. Okay, so I'm talking about the sodium carbonate step here. So, you know, we've got our reaction happening here, what acid is reacting, you know, what salt's being produced, what happens to that salt, does it stay in the aqueous layer, all that kind of stuff. All right, use your carboxylic acid, why the salt is highly soluble, so you can talk about dissociation, ion dipole interactions there. You know, why does that salt not solidify? Why doesn't it precipitate? So we can talk about some solubility stuff there as well. What's the point of the calcium chloride step? So the dehydrating agent, so the fact that that basically absorbs the water. So explaining that as best as you can. And then talking about that loss of yield. So there are 2 points here. There are many other factors that we could talk about here. Remember, we're not talking about random systematic error. Here we're talking about why is our yield lower than expected. So you're not going to get that. I think it's 65%. You may need to research it. Why aren't we getting that level? If you get over 65% yield, you've stuffed up your calculations somewhere. Okay, so why are we lower than that? Linking to aspects of the experiment. So this is the part that you really want to focus on, because there's a whole section of the rubric that's about that. So this analysis and evaluation is all about critically and logically evaluating procedures and suggesting a range of improvements. Improvements are easy. You basically just want to look up some Fisher esterification on the internet and then figure out what do they do that we don't do, and then why does that make the experiment more successful. Okay, so it is a lot of work. I'd like to have the practical by Monday. We can't really dawdle on this because we do have a fair bit of stuff to get through still with the course. And we're basically going to be working till week 1, term 4. So if I get this by Monday, I can quickly draft it and then give it back to you. If you have any questions, make sure you email me, because I'm not going to see you guys till Monday. And we'll see how we go. Thanks very much.